All right. So, uh, in the last class, we had done the critical current of a wire. Then we had where is the echo? Yeah. And we had compared that expression with various other situations. Simple estimate based on just condensation energy and equating that condensation energy to the kinetic energy, to Josephson junction, and so on. So, before we take little parts, which I have mentioned to you before, let us continue a little bit more with thin wire. But now, what I will take is not just thin wire, but really very, very thin wire. So, how thin a wire? So, there is a group doing the video project. I hope you are all working on your video project, by the way. So, there is a group doing the video project on small particle, nanoparticle, and nanowire. Can you remind me who they are?
Yes, sir.
Uh,
So,
yes, go ahead.
Gorachan,
Jyoti and Devjyoti.
okay, Gorachan and Devjyoti. Okay. So, you had, so the nanowire part of your project, I will explain today the basics of that. Because that's something that will directly come as an outcome of the Ginzburg-Landau theory. Alright, so before that, let me first try to see if I can show you what I am talking about when I am talking of a nanowire. So let me open something. Okay. Okay, so with the advent of nanotechnology, it has become more and more important to make smaller devices, and for superconducting electronics, for example, Josephson junction electronics, qubit, or for example, superconducting hot electron bolometers, you have to make small devices, and those small devices will also have small superconducting contacts and very thin superconducting contacts, nanometers in the tens of nanometers, let's say, in dimension. And therefore, it's important to know when you make these, when you take a strip of a superconductor, which is, let's say, tens of nanometer in dimension, will it have any additional phenomena that will come in, particularly fluctuation effect. Now, these theories were developed quite long back. In fact, after Ginzburg-Landau theory, people started playing with all these kinds of things, and this theory of fluctuations in superconducting nanowire was established for several decades. But the experiments that were done earlier were on micron-sized wires, where the fluctuation region is extremely narrow and close to Tc. So it will be, let's say, few millikelvin around Tc. Now, who cares about what happens few millikelvin around Tc? But now that we can go to much, much lower dimensions, this fluctuation region increases and encompasses a large part of the superconducting temperature range. So now it's something of practical importance and you can no longer ignore them. So the modern study of these superconducting nanowires, the group that had mostly done these experiments was mostly started these experiments. Later on, many people did. Was this Bezriadin's group in Urbana-Champaign, and what they were doing is they on silicon substrate, let's say, they were using lithography to produce this kind of a trench. And then you place, initially what they were doing is they were placing DNAs on that trench. DNA here has no biological significance whatsoever. These are essentially dead strands, if you want. And what they were doing is they were depositing a superconductor on this DNA. So this DNA just act like a support for the superconducting nanowire that you are depositing on it. So DNA was very good for them because DNA was insulating. They also did the same experiment with carbon nanotube, but carbon nanotube has some conductivity. So therefore, when you put carbon nanotube in proximity with a superconductor, there is proximity effect that comes in. Okay, so then you deposit a superconductor. So you have this superconducting nanowire here. And then you put your electrical contacts on this side, and you measure the resistance of this nanowire. What do you see? So what you see is given here. So you see, this is the cartoon of my nanowire, and actually these contact pads that you have on the to make electrical connection on the nanowire, these are also superconducting. So what happens is when you cool and measure the resistance, initially you see this abrupt jump, but this jump is not related to the nanowire. This jump in the resistance is actually the superconducting pads going superconducting. Then what you measure is, so once the superconducting pads are there below the TC, the resistance is zero because these are large pads. So therefore, now what you are left with is just the resistance of the nanowire. And that you see varies in a very strange fashion. It does not abruptly go to zero as we know any bulk superconductor should, but it forms this long tail, it decreases, and beyond a point it might go below your resolution limit of your measurement apparatus, but it does not really go to zero. So if you take very thin wires, then it actually does not go to zero. It becomes small. In many cases, it will go below your resolution limit, but it's not an abrupt resistance that is going to zero. So people realized, they made, so experimentalists of course don't rely on just making one sample and doing a measurement. That's bad experiment. You make many measurements on many samples, and then you try to improve your sample so that you don't have inhomogeneity, so that you don't have impurities and so on. And when they did that, they realized that you can never get rid of this long tail if you are in very thin nanowire. So there is something fundamental there. There is a physics involved in this tail. It's not a tail that's just appearing from impurity effects or effects of inhomogeneity. So now what we will do is we will try to understand this long tail behavior by trying to see what are the physical mechanisms that can give you a finite resistance below TC in the case of a superconducting nanowire. So let us go back to our one node. Where is the one node? Yeah, it's here. And let me take this problem of superconducting nanowire. All right. So I have a very thin superconducting wire, and these wires typically I will give you an assignment problem where you have to estimate how thin the wire has to be to observe the kind of effects that you have just seen. But let me give you an idea. It's actually tens of nanometer. It's 10, 20 nanometer. That's when you will see this effect. All right. So therefore, needless to say that the diameter of the wire is really small, and it's much smaller than the coherence length. Now, what can happen here? Suppose I have see, you know that the phase of the superconductor is the same everywhere. So that is correct. Over the entire wire, the phase suppose is theta. But now these wire, if I take a segment which is of the order of the coherence length, then the condensation energy in this segment, that will be given by half on n0 delta square. Let me call it EC, that is my condensation energy. So therefore, the segment condensation energy would be A is the cross section of the wire into EC. Now, this is the free energy cost between the normal state and the superconducting state. So assume that this free energy cost is not very different from kT. Okay? In that case, thermally, there will always be a probability that this segment for a short time will become normal. So if this segment here becomes normal, if this segment becomes normal, then this superconductor and this superconductor momentarily, they are no longer connected, so they become two superconductors. So now I can have something which is theta 1, or if you want theta left and theta right, they can have different phases. However, and once they are different phases and they are disconnected, the theta L and theta R can be anything. They have no reason to have any connection with each other. However, This region is only momentarily going normal. So what happens when it becomes superconducting again? Because it's a fluctuation effect. It's just a Maxwell-Boltzmann fluctuation. When it becomes superconducting, immediately L and R has to again lock to the same value. But in between, if L and R has moved, let's say, by an amount which is more than pi, then instead of coming back to 0, it will flip over to 2 pi. This is a very important concept. Anyone who is not following, ask. See, this, when it is momentarily normal, if theta L minus theta R becomes larger than pi, then after recovery, theta L minus theta R will become 2 pi, which means that with respect to theta L, this theta R has undergone a full phase rotation of 2 pi. And you know that for anything, for any physical quantity, 2 pi and 0 are the same. So therefore, once it has rotated by 2 pi, it's again in the phase coherent state, because the system, when it has rotated by 2 pi, it does not know whether it is at 2 pi or whether it is at 0. It's entirely the same thing. Unless you have a Berry phase and so on, let me not get into that here. Those are more complicated things. However, the process of this rotation of 2 pi will have an implication. Can anyone tell me what that implication would be? What would be the implication of the rotation by 2 pi? Do you recall the Josephson relation that we have derived? The second Josephson relation, if there is a rate of change of theta, then there is a voltage. And that voltage is actually H cross by 2E d delta theta dt. Delta theta is nothing but theta L minus theta R. So during the process, when this phase flipped by 2 pi, there was a d delta theta dt. Otherwise, it cannot flip. That means this will generate. So this process is called a phase slip when it rotates by 2 pi, and this implies that the phase slip will generate a voltage spike Okay, so that means you will momentarily generate a voltage spike across these two segments, and if you are measuring from two ends, you will see that voltage spike. However, if your wire is long enough, then you will not have one such process. You will have many such process, sometimes here, sometimes here, sometimes here. So at what frequency is something that one has to do the microscopics and calculate, but this is actually something that people have calculated with Ambrikhaukar-Halperin formula. But nevertheless, the point is that you will have many such spikes happening at different times in the on this wire, and therefore you should have in principle measured a net voltage which is the average of these spikes between the two ends. In the absence of current, it will produce an average voltage V. However, in the absence of a net DC current through the wire, which means if I DC, I will not write DC later on, I will just write I, but here I am clarifying. If IDC is 0, then the voltage will be 0. Can anyone tell me why? I just told you that you will have many voltage spikes that will happen because of these slits. But now I am telling you, if I don't apply a net DC current here, the voltage across this wire that I will measure, let's say with a multimeter, will be 0. Why is that?
So will the rotation of the phase, this will be neutral? I mean, total will be neutral. Some will be 2 pi and some will be in the other direction, the phase rotations.
Yeah, that is exactly correct. Some of them will be 2 pi, some of them will be minus 2 pi. So some will rotate in this direction, some will rotate in this direction. And one of them will produce a positive voltage spike, the other will produce a negative voltage spike. So the average would be 0. All right. However, what we are interested is not when the current is 0, because resistance means the voltage that appears when I pass a current. So now let me try to calculate what will be the voltage when I apply a current. Okay, so now suppose I take a current source and I pass a current IDC equals to I through the nanowire. All right. So what is the work done? Let me calculate the work done. you know that this will be IV dV dt, and I also know, oops, okay. Uh, I also know from the Josephson relation that V dt is H cross by twice E d delta theta. So then this quantity will become and now here I was integrating over the time it takes for one phase slip, and now this quantity, it will depend on whether I have a positive phase slip or a negative phase slip. So if I have a positive phase slip, then I will have to go from 0 to 2 pi, and if I have a negative phase slip, I will have to go to minus 2 pi. Accordingly, what I will get is H by 2EI or minus H by 2EI, and this is for a positive phase slip, that is what I write as PS, and this is for a negative phase slip. Okay, the important point is that now you see the work done on the system for a negative phase slip and a positive phase slip is different. Because of course in one case the voltage is actually helping the current, and in the other case the voltage is opposing the current. So therefore now if I take any segment like this, earlier the segment to become normal, the free energy barrier was F, which was given by this quantity, condensation energy into the unit volume of this area. But now it will also depend on the current, and depending on whether it's a positive phase slip or a negative phase slip, the energy required to drive this segment to the normal state will either be increased or decreased. So therefore, this implies that I have here a delta F, that is the difference between these two energy, H by E into I, that differentiates between the free energy cost for exciting a positive phase slip and the free energy cost for exciting a negative phase slip. All right. So the rate of phase slip when I was 0, that is given by some constant. This constant is something I do not know. I need microscopic theory to calculate it, but this, it was proportional to e to the power minus f by kt, and this was true for both positive as well as negative phase shifts. When I is not equal to 0, then the effective rate. Now, what is the effective rate? The effective rate is positive phase slip minus negative phase slips. So that is number of positive phase slips minus number of, actually I should take negative because negative are more populous. So I will get into sign. Minus number of positive phase slips. So this is actually the offset, because the one that cancel with each other, they are not producing any voltage. I don't need to bother about them. So this will be the same rate. Now here, in one case I reduce the barrier, in the other case I increase the barrier. So this will be, this is the total rate of change of phase that I will measure at the, if I measure at the end of the two wires. So now I am looking at one end of the wire and the other end of the wire, and I don't need to care where the phase slip is happening. I am seeing how much is the rate of change of phase between this end of the wire and that end of the wire. So this will be given by the total number of uncompensated phase slips. This is here. So this quantity is nothing but twice omega e to the power minus f by kt, and then I will have sine hyperbolic delta f by twice kt. All right. So I know that if I have to calculate now the voltage between the two ends of the wires, not the voltage from one phase slip. So if you, what do I write this? VT, V total voltage across the two ends of the wire is H cross by E, and that will be Okay, so I have been able to calculate the current voltage characteristic of a superconducting nanowire in the below TC. Now you can see first thing is voltage is not zero. So unlike a bulk superconductor, here because I have this phase slips, I will never have a situation where I will pass a current and not produce a voltage. I will always produce a voltage. So in a superconducting nanowire, you can never realize a true superconducting state. So by which I mean a true zero resistance state. Nevertheless, let us now, we have seen that it was forming a long tail and then decaying exponentially. So to understand that, take the limit of small I, small current. So for small current, you can linearize this equation and then you will have the voltage which will be H cross squared pi omega by E squared. Kt then e to the power minus f by kt here into I. So now you can divide both sides by I and this is how the resistance will vary. So you can understand if your F is of the order of Kt, then you will have a tail and the smaller F will become, you will have this longer tail and in the limit of a very, very thin wire, you can have this tail which, so you will have a true zero resistance state only at t equal to 0. At t equal to 0, of course, R is 0. So R equal to 0, only at t equal to 0. Alright, what I have calculated here is what is known as the thermal phase slip. Now there is another effect which actually comes from quantum mechanics, that comes from the quantum mechanics uncertainty principle that can even prevent the resistance to go to 0 even at t equal to 0. So the quantum phase fluctuation, let's say in a nanowire or in a Josephson junction, is something that we will deal with later on. But this is the basic origin. The omega here you have to calculate it from microscopics. You cannot calculate it just from phenomenological Ginzburg-Landau. Let me just see if it is there in the book. So, and to what extent it's there. But Godachand and Devjyoti, so this is the background of what we will have to now cover in much greater detail. Any question on this part?
Yes, sir. I have a question. So am I audible?
Yes, tell me.
So when the small segment after recovery,
Yeah.
there is a phase a difference of 2 pi between the two superconductors.
Can you speak louder? I have a
Yeah.
difficulty in
Yes, sir. So after recovering, there is a phase difference of 2 pi. So instead of being at the initial condition, they differ by a phase difference. So what is the reason behind that phenomenon, this phase slip that is making that phase difference of 2 pi? I mean, they instead of reaching at the initial condition, they are having a phase difference of 2 pi.
Phase difference. How much is the phase difference?
It's 2 pi. They are rotated. The theta has been rotated by 2 pi.
Is 2 pi a phase difference actually? Any trigonometric function, can you differentiate between sine 0 and sine 2 pi or sine x and sine 2 pi plus x?
No, sir. They are same. Yes.
That's the point. When you are rotating by 2 pi,
Yes.
you are coming back to 0.
Yes.
But the process of going over this 2 pi is it has to be through a rate of change of theta.
Yes.
You understand? So
Yes.
once you have rotated by 2 pi, you are back to the same place.
Yes.
Rotating by 2, once phase difference of 2 pi and phase difference of 0 is the same. Actually, in principle, you can have also 4 pi, 8 pi, any integral multiple of 2 pi. But the point is that those processes will be less and less likely because within the same time frame you will have to rotate by 4 pi, which is less likely than a 2 pi phase shift. That is one of the things. The second thing is that if you really have a 4 pi process, you can always consider that as 2 pi
2
process.
pi rotations. Yes.
Okay. So a double phase shift is actually 2 single phase shifts.
Okay. Thank you, sir.
Okay. Any other questions? So, see, these are things that what I am showing you is that this Ginzburg-Landau, despite being a purely phenomenological theory, it has spectacular predictive power. Means this is an effect which is entirely a quantum mechanical effect that you are able to simulate essentially through Ginzburg-Landau. Okay, so the prefactor is something that you have to do microscopically. It is not done in Tinkham's book, but there is a discussion and the final form is there. You can go to the original papers and try to see how difficult or how easy the derivations are.
Okay, sir.
Okay,
Hello, sir.
so
Sir, you have said that theta L minus theta R, when it is greater than pi, then after recovering, we are getting the phase difference to be 2 pi.
yeah,
But what happens if that is less than pi at the
then it
beginning?
will come back to 0. See, it will
Okay.
go in your free energy. 0 is the minima and 2 pi is
Hmm.
another next minima, 4 pi is the next minima, and so on.
Okay.
So,
Okay.
okay, let me. These are concepts that are better clear now. So, if I plot the free energy, as a function of delta theta, then of course 0 is a minima. All right?
Yes, sir.
And then the next minima is at 2 pi. This is not sinusoidal, it's just periodic. That's all. Next minima is at 4 pi and so on and so forth. So if it fluctuates less than pi, then it will come back here. If it has fluctuated up to this point, then it will come to the nearest minima. If it has gone here, then only it will go to this minima. Is that clear?
Yes, sir. Yeah, got it.
Okay. So
Thank
actually this is why, for example, you can always, if you take a thick wire then you should think that you will still have some probability of phase slip. Well, you will always have some probability of phase slip. That probability might be 1 in the lifetime of the universe, so you don't care. But nevertheless, the other reason is that in a thick wire, your fluctuations that will push the delta theta to the up to this point greater than pi will be less. Most of them will be fluctuating here. So effectively they will fluctuate in this small region here, and they will never cross over to give you a total phase slip here, which is 2 pi. And small fluctuation close to the bottom does not matter because they will cancel out. When it goes in one direction, the rate of change is positive. When it goes in the other direction, the rate of change is negative. It's only when it crosses the barrier, then it has a net movement in one direction. It has a net rate of change in one direction. Okay, so now let me go to another effect. So, Ginzburg-Landau theory is an experimentalist favorite because it allows an experimentalist to sort of, there are wide variety of physical phenomena, not all by the way. You cannot explain tunneling with Ginzburg-Landau theory. That's not possible. You have to go to VCS. But on the other hand, there is a wide variety of phenomena that you can try to understand based on Ginzburg-Landau theory. So there is another very interesting phenomena, and now let me show you some data of ours because this is something that we had played with at some time. Okay, so let me first explain to you here the phenomena because otherwise it will not be clear what I am plotting. So the other next phenomena that we will deal with is little parts effect. So these were the early days of superconductivity, and people were fascinated with superconductivity. Some people like me still are, but they were in those days playing with simple things and surprisingly getting very interesting phenomena nevertheless. So what little and parts were doing is this, that they took a quartz, a small quartz fiber, and then can you see what, have I shared the screen? Can you see what I am writing?
Yes, sir.
Okay. And they coated the surface of this quartz with a superconductor. Not the top. So now the superconductor is like a hollow cylinder. And then they applied a magnetic field. And what they observed is something very funny. They observed that the superconducting transition temperature Tc as a function of magnetic field has a nice periodic variation. Well, this I am exaggerating, The effect that they saw was extremely tiny. I'm exaggerating because the effect that we see nowadays, again, thanks to nanotechnology, is much larger. So I'm just trying to see how much effect they saw. Okay, I don't have it here. I'll share the original paper. It has a nice periodic variation with magnetic field. Perfectly periodic. And then they tried to see what is the period. So what is the period delta H? If you have such a nice periodicity, then this period should have some meaning. And then when they multiplied that delta H with the area of this quartz, the cross-sectional area of this quartz fiber that they were using, they realized, so this is, suppose this has a cross-sectional area A, they realized that delta H into A is exactly one flux quantum. So something is happening, and one flux quantum, it is actually H by E. Sorry, H by 2E. Okay, so now the original paper of Little and Parks, I don't have it with me. Let me show you some effects that we see in modern experiments. Okay, so in modern experiments, often what one does is, instead of taking a superconductor with just one hole, so this was like one ring, what we take is something which is of this form. So this is, if you want, a superposition of many little parts, but this has the advantage that it allows you to measure things much more accurately. So you take a superconductor and you have these holes here. So these holes are roughly a hexagonal array. Here in the, for specific reasons, they are not exactly hexagonal. So, but you have nevertheless many holes. So you can consider as if, so around every hole you have a superconducting ring, and then you can consider as if you have many such rings. So what we will see is a linear superposition of what will happen in each of these rings. So interrupt me if you have any difficulty. Okay. Okay, this is what you see. So what I am doing is, instead of measuring the variation of Tc, that is more difficult because you have to then do this resistance versus temperature measurement for every magnetic field. Instead, what you do is that you come close to this transition region and then you sweep the magnetic field. If the Tc goes up and down, then the resistance in this transition region will vary periodically and will have a large variation, and that is what you measure. And this is what you see. You see again this periodic variation, and if you calculate, then this delta H into the cross-sectional area of these holes will again give you exactly one flux quantum. So these are some more similar data, and I think somewhere there is the TC variation also. Let me just check. Yeah. So here you have the TC variation. So these are not very dense data because, as I told you, you have to do many temperature sweeps, resistance versus temperature, but nevertheless, you see roughly the same pattern. But here the periodic variation is clear. Okay, so how does one understand these phenomena? Okay, so the complete derivation of the phenomena, we will leave it for the next class. But let us physically understand what is happening. You have a superconducting ring and you are applying a magnetic field. Now you know that you have read about flux quantization, and you know that the flux inside this ring has to be an integral multiple of a flux quantum. So therefore, the flux has to be an integral multiple of the flux quantum. But if this cross-sectional area is A into H is your applied magnetic field. This is in the absence of this ring. This is the flux that would have threaded through this area if the superconductor was not there. Now, since I have put the superconductor here, I am forcing it to be close to one of these integral values, 0. Then at some point it has to jump to 1 flux quantum, then 2 flux quantum. Now, how does it do that? What it does is that when I am putting any arbitrary H, then there is a supercurrent JIS that is flowing in this ring that compensates and brings the flux inside the ring to an integral value of the flux quantum. So when this condition is satisfied, then my supercurrent is 0. And when this condition is not satisfied, then this supercurrent is non-zero. Now, if there is a supercurrent, that means there is a kinetic energy of the Cooper pair. If there is a kinetic energy of the Cooper pair, that means that the condensation energy will proportionately come down, and therefore it will be easier to destroy the superconductor. In other words, the superconducting transition temperature will come down. So that is the physical origin of this periodic variation. So on Wednesday, we will use Ginzburg-Landau and see how one can reproduce this curve quantitatively. So we will do the Ginzburg-Landau solution of what we have done here, just using ones. Okay, so I will stop here. I have exceeded my time. And let me take any remaining question that you might have. Any other question? Okay, if not, let me disconnect and we will continue on Wednesday. So, in the beginning of this Ginzburg-Landau theory lectures, what we are doing for few classes is to take up this kind of physically important but simple problems. After this, we will get into deeper analysis of Josephson junction, and that is going to be a full-fledged topic on its own.